Welcome to our exam prep course. I'm Charles Fulmer, and we're going to walk you through the code book. First, we're going to start out with Ohm's Law. We're here to help you pass your test for the first time. And if you do not pass it the first time, we'll work with you until you do. There's a few things you got to do on your own. First, we ask that you do the entire workbook, do all the tests and quiz that we give you, follow our instructions, the highlight key words and numbers in the code book, not whole paragraphs. For instance, here is the 2020 electrical code book, and as you can see, we just highlighted keywords and numbers. 1500 volt amperes for small appliance load, laundry load, 1500 watts, so forth. So this way it sticks out to you, and you don't have to read the entire paragraph. We also will be looking at different calculations in the code book, and 220 is full of them. Our contact information above, our website, our email address. You can shoot us an email at any time. Our phone number is posted on the screen, and our office hours, if you want to talk to someone in person, is Monday through Thursday. We're closed Friday and weekends, and we're here from 9 a.m. to 4 p.m. Okay, and then we'll help you walk you through anything that you don't quite understand, or you see something different than what you've been taught. We'd be glad to walk through it with you. So, like we said, you need to have your code book ready. It needs to be tabs. You will just be wasting your time without a tab code book if you try to take the test. Highlighter pen. We suggest you highlight everything that we kind of go over. We won't go over everything in the code book. The workbook will also cover just the main things, mostly the changes and the majority of things that we've seen on the test for the past 16 years. We've had a very good pass rate. Everyone that's took this course for their masters has passed the test the first time. So we have 100% with that. In the journeyman, we're probably at a 98%. We've had 3 or 4 guys in the last 16 years. We had to work with them a little bit, and they went and passed it the second time. Also, you need a notebook or a scratch pad and a pen and a calculator. All you need is a square root key. You don't need nothing super fancy. Matter of fact, a lot of the testing sites won't let you in with a contractor's calculator. Okay, so like I said, just some simple math, kind of refresh you. You may not have done this in a while, but we've got to always change the fractions over to whole numbers. And it's really simple. You take the lower number and divide it in the upper number. We'll be working a lot with 1/4, that's 25%. Half is 5%. And 1/3 is 0.333. And so, like I said, we need to change it over to whole numbers. A lot of guys mess up when they're doing their calculations because they get the percentage decimal in the wrong place. With the percentage sign, this is what it looks like. Without the percentage sign, you always go over 2 spaces, 2 numbers. Okay? In other words, 80% here would be 0.8, 125% would be 1.25, and again 50%, 0.5. We'll take the Ohm's Law wheel, we broke it down into 4 parts, so basically that's what it is. First thing you have to determine is what you're looking for. Am I looking for amps, watts, volts, or ohms or resistance? And then each one has 3 calculations, and then you use the calculation on what values do you have. For instance, here you got volts and amps, which is easy. Amps divided into volts gives me my resistance, and then you got some of the more complex ones. We're going to go over these. First, let's look at resistance. Okay, so here's our 3 formulas. and we have determined the question wants us to find the resistance, okay? And so to find the resistance with watts and amps, it's going to be watts divided by amps squared. The little 2 is a square, so that would be 30 times 30 divided into 7,200. We suggest you always do your multiplications here first before you do the division. And as you can see here, we're going to be using the same values just so you can see how this all works forwards and backwards. 240 volts, 30 amps, and 8 ohms. And so you do these calculations. Now, and that's another thing we want you to do. You're sitting there with a calculator and a scratch pad. Punch these numbers in. See if you come up with the same thing. You stand back and just watch us do these and don't practice them. You know, you're going to be shocked that sometimes you can come up with a 0.8 or 8.2 or whatever, but just because you did not put the decimal in the right place. Here, basically, same thing. We're using 240 volts, and using these 3 calculations, all 3 would come out with the same wattage. You've got 7,200 watts when we took volts square, which is 240. 240 times 240 equals 57,600. Divided by 8 equals 7,200 watts. 240 times 30 amps, 7,200 watts. So it just goes on. Again, you can practice with these. Now, this is the one you've watched for. You may be a little rusty on. Here's where the square root key comes in. Every time you see a calculation with a square root key over it, that is the last thing you punch to get your answer. So in this case here, we've got the 7,200 watts times 8 ohms equals 57,600. Hit the square root key, comes out 240 volts. 30 amps times 8 equals 240 volts, and then 72 watts divided by 30 amps is 240 volts. Okay, and you have one other like that in amps. Okay, here we come up with our equation each time. 30 amps, 240 volts divided by 8 ohms, 30 amps. 7,200 watts divided by 8 ohms equals 900. Hit the square root key, 30 amps. Here's a couple examples here, and they're also in your workbook, and kind of see it in what we're dealing with. Here's our 240 volt motor. We got a 30 amp load. We got 8 amps resistance of the wiring here. Okay, and so we worked out the equations here so you can see how that turns out. Here's one in the questions. What's the amp? So we're looking for the amps. Okay, it's an easy one. We got 10,000 watts, 10 kW. Anytime you see a K, that's 1,000. So 10 kW, 10 kVA. That's actually 10,000 watts divided by 240 volts, 41.6. Now the code of 220 tells us to round up from 0.5 up, and then anything under 0.5 drop. Now when we're doing the math equations, leave the point number value there. Don't leave all the numbers, this first 1 or 2 there. But when we get through, look at our answer key, and if our answer offered to us is 42 amps, and then we'll use 42 amps. If it's 41.6, then we know that's what we came out with. Plus, there's no breaker, 42 amp breaker, so we'd have to go up to a 45 amp breaker anyway. And down here, as you can see, we get in the ohms. I left it at 41.6, so I get my ohms, my ohms is 5.7, and I use the 5.7 again in finding the wattage. Okay, and this is the wattage that's been consumed. We've got 10 kW, so this was not a very efficient piece of equipment here, and we're coming out with 10,105 watts that are being consumed. You're also going to need to know that when you're doing all three-phase calculations, you want to use the square root of 3. So we put this little table together for you to use. There's probably some numbers that you probably want to try to, maybe you don't have to memorize them, but just never forget the 1.732. That is the square root of 3. You punch 3 in your calculator and hit square root key, and it'll give you 1.732 and a series of numbers, but we always work with 1.732. For instance, single phase, simple. Looking for the amps, you divide the volts into the watts, gives you 41.6. But when we do three-phase, then we have to take the 240 volts and multiply it by the square root of 3. So this is a given, and this is where a lot of guys mess up on the exam. They know divide volts into watts to get amps, but they forget on three-phase you got to do the square root of 3. So 240 volts becomes 416. You divide 416 into 10,000 watts and 24 amps. Now, just for your information, if you'll notice, single-phase motor and the three-phase motor were both pulling 10,000 watts. Takes less amps to operate a motor on three-phase, but when it comes paying the electrical bill, it's going to be the same because you pay for the wattage. Okay, so just kind of throw that out there. 24 amps. The advantage of using the three-phase is smaller wiring, smaller breakers. Okay, and also we got here 10 kW motor. 480 volts pulls how many amps? 10,000 watts divided by square root of 480, or square root of 3 by 480 equals 10,000 divided by 831. That's 12 ounce. Okay, on our overcurrent devices, the breakers are designed to operate on a continuous load at 80%. If you don't know that by now, a continuous load is anything that stays on 3 hours or more at a time, and usually that's lighting and some equipment. And so if you've got a load it's a continuous load, you always multiply it by 125%. Now 80% is the reciprocal of 125%. I wish I put my example of 100 amps. You got a 100 amp breaker. What's 80% of a 100 amp breaker? 80 amps. 80 amps times 125% is 100 amps. Okay, 80 times 125% is 100 amps. Okay, well here my example is 60 amp load. It's a continuous load. I multiply by 125%, comes out 75 amps. We go to 240.6 and we'll see that there's not a 75 amp breaker. We have to go to an 80. Okay, so 80 amp breaker. Okay, what's 80? Is that 80 amp breaker big enough? We did 125%. So if we go at it backwards, 80 times 125% is 64 amps. So an 80 amp breaker can take a continuous load up to 64 amps. I use 20 amps for an example a lot too, because you got a 20 amp breaker, you can load it up with receptacles, but a 20 amp breaker and you're putting lighting on it, you only want to load it up to 16 amps. 80% of 20 is 16 amps. Here is 208 volts. Now we got a 3% voltage drop. Now the code recommends no more than a 3% voltage drop from the branch circuit, and no more than 3% voltage drop from the meter to the panel, and overall from the meter all the way to the device no more than 5%. So when we're running our electrical wiring to a motor or something, we don't want more than a 3% voltage drop. Okay, so what is the voltage drop on a 208 voltage circuit? 208 times 3% equals 6.24. We do not want that to drop below 6.24 volts. Okay, you take 6.24 volts from 208, you've got 201 point, or actually 202 volts. Okay, here we're going to have a power loss because of the voltage drop of 6.24 times 18. Voltage drop times amps equals the power, and you've got a 112.32 watts of power loss. Determine voltage drop with Ohm's law. Here we've got 0.2 ohms resistance returning. We've got 0.2 resistance going to. That gives us a total of 4.4 ohms resistance. Okay. Now we'll talk about this in chapter 9 at the end of the second video. But in chapter 9, table 9, 1,000 foot of number 12 has a resistance of 2 ohms. Okay, so we got only 100 foot here. So we take the 1,000 foot divided into 2 ohms. That comes out 0.002 ohms per foot. Okay, so we got 100 foot each way. So 100 foot or 100 foot times at 0.002 comes out to 0.2, and we multiply 0.2 or add 0.2 to 0.2. Like I said earlier, this is 4.4 ohms resistance. Okay, so we take the amps times the resistance, and that gives us the voltage drop. Okay, so we know that if we take a reading here and it's 120 volts, then it's going to read 113.6 here. Bad thing is, if this is already like 115 volts instead of 120, then it's going to be less. Here's a little chart to remember, easy to remember. Probably the one you'll use the most out in the field. Watts. Pi, this is pi, P-I-E, it's round. Whatever we're looking for, P's on top, so if we're looking for E, you divide I into P. If we're looking for I, you divide E into P. If we're looking for P, we go I times E. Pretty simple. Just cover up whichever one you're looking at, and that's the formula that you'll use. Here's one for resistance, E over IR. I times R gives you E. R divided into E gives you I. I divided into E gives you R. Here's a simple one for resistance. What is the resistance here? Is 144 ohms. So the longer the wire, the more resistance we'll have. So the amps is volts divided by resistance. We are pulling 0.83 amps here. Calculating efficiency. Output over efficiency input. And here we're asking what's the output. The input's 330 watts. Okay, we take that times it by the 90% efficiency. There's 279 watts output. Turn this around a little bit. You've got efficiency. What's the input? Because our output is 297 watts. And we do the math, and 297 watts divided by 90% equals 330 watts input. Power factors. Watts. We can take the volt amps divided into the watts, give us our power factor. We've got a ballast here is 100 volt amp output for 240 watt lamps is 80 watts. 80 watts divided by 100 volt amps rather equals 80% or 0.8. ARCA 220. Now there's a big change in the 2020 code, 220.12. For instance, if you look here at offices, it used to be 3.5 volt amps per square foot. So here is the table we use to wire to figure out the meter size, the load size for any facility. Okay, this is just an example. Always look at the tables in your book. This is 220.12. Now we're going to talk about this D right here that's with offices, and well, that it's banks and offices. This applies, this little rule will apply to banks and offices. First we look at, in commercial, unlike dwelling units you can put as many receptacles you want on a 20 amp circuit. But as far as commercial, you got to figure 180 watts per yoke or strap. Now that's what they're calling these ears. They don't call these ears in the code book. They call these yokes or strap. So no matter how many plug-ins, now unless there's a rule on if it's got more than 4 plug-ins, if it's got 5 plug-ins or so, then you calculate 90 watts per plug-in. But 3 plug-ins here, 180 watts. Duplex, 180 watts. Singleplex, 180 watts. Okay. How many receptacles can be on a 20 amp commercial circuit? Now, here's something I want to remind you of. You're taking this test based on the National Electrical Code, not your city code, not what your inspector makes you do. Okay. Now the city code you may be used to 8 to a 20 amp circuit or 6 to a 20 amp circuit, whatever you're used to. You just got to throw that out the window. You go by what the National Electrical Code says. We're allowed 180 watts per yoke. Okay, so how many receptacles can I put on a 20 amp commercial circuit? 120 volt by 20 amp breaker is 2400 watts. Okay, and this gets me. I ask a lot of guys, how many watts is a 20 amp breaker good for, and they're just lost. Okay, the Ohm's law, simple stuff. You take volts times amps, volt amps, gives me my watts. Okay, all right. You divide the 2400 watts by 180 watt per receptacle. That gives me 13 receptacles per 20 amp circuit. And I've seen this question on the Masters and Journeyman's test. When I was in Texas, I had to take the Journeyman's test. I also took the Master's test. Here in Arkansas, I had to take the Journeyman's test again and the Master's test, and I've seen this question quite a few times. Matter of fact, the Master's test in Texas, I had to do an entire building calculation from top to bottom. All right, so here it is, 220.44. Now, we can figure 180 watts per receptacle for the first 10,000. Okay, this little table, look this up in your code book and kind of highlight it, 220.44, just 2 little lines. And the first 10,000 at 100%, the remainder over 10,000, 50%. So here's an example. 150 receptacles at 180 watts equals 27,000 watts. So I like to work with 2 columns. This is what I call my whole numbers. I put a column to the right of my scratch pad. So off the bat, I take 10,000, put it over here. Okay, The remainder, you take 10,000 from 27,000, and you've got 17,000 left over. So you take the remainder at 50%. Go back to my column over here, and you got 8,500. So what is the load? The demand load for 150 receptacles? 18,500. Now, here's where we're getting to that B that was on the bank. 220.14K tells us the receptacle load for banks and office buildings shall be the larger of 1 or 2. 1 says the receptacle shall be calculated at 180 watts per receptacle, or yoke, applied the demand factor of 220.44, which we just did. Or the receptacle load calculated at 1 volt amp per square footage. Which one is the larger? So this is going to require a little calculation. We got a 20,000 square foot bank. Well, 2 is easy. 20,000 times 1 is 20,000 watts. Number 1, we're going to have to take the 120 outlets, multiply 180 watts, and it comes out 21,600. First 10,000, okay, at 100%. The remainder at 50% is 5,800. We've got 15,800 watts. Which one's the larger, 1 or 2? 2, 20,000. So you would just throw the receptacle load away and use this one. Always use the larger of these two. 220.14F. Again, these numbers, every time you see one of these numbers pop up, go there, highlight it, highlight sign outlet, highlight 1200 volt amps, highlight at least 120 amp. That's it. Okay? A lot of times when I was an electrical inspector, there was buildings that did not have, especially like lease malls and stuff, that didn't have a front sign. You still have to calculate in a 20 amp circuit for this sign, and it got to be no less than 1200 watts. And one of the trick questions, and it gets me when people say, oh, trick questions. All questions are trick questions. One of the things I see is, what is the calculated load for a 1,000 watt sign? Well, it's going to be 1,200 watts because that's the minimum. That's a 1,600 watt sign, then the load is going to be calculated at 1,600 watts. Show window lighting. Again, 220.14G2, 200 foot. Well, actually, you want to highlight 200 watts per foot, and so I've got, even though I'm going to have maybe 10 foot of lighting in here, we go the width length of how much show window we got, how many feet we got. 20 this way, 10 feet this way. That's 30 feet times 200. We've got to calculate in our calculation for a commercial building, show window lighting, 6,000 watts. Here's another trick question. 220.14H, multi-assembly outlets. Now these come everywhere from 2 feet apart to 6 inches apart, 12 inches apart, whatever. It doesn't matter. The two key words you're going to be looking for here is unlikely and likely. Okay? Unlikely, you got to calculate 180 watts per 5 feet, or fraction of. In other words, 10 feet here is going to be 180 watts. If this was 6 foot, 280 watts. 7 foot, 8 foot, 280 watts. If this was 11 foot, then it would be 3 times 180 watts per fraction. So every 5 foot and a fraction thereof, you're going to calculate 180 watts. That's unlikely to be used simultaneously. Likely to be used simultaneously is per foot. Now here's the other thing. Every time I've seen this question on the test, they had both answers. Here we got 10 foot at likely, 10 foot at unlikely. The answer here is 360 watts. The answer here is 1800 watts. Both of those answers may be there, just to see if you know if it's per foot or per 5 feet. 220.43, show window track lighting. Show window and track lighting. Now, we did the show window. Track lighting is 150 watts for every 2 feet. So this is a little tricky here. Every 2 feet. You know, I don't know where these engineers come up with all these numbers. Just learn to highlight these and work the formulas. Here we go. 20 foot. 20 foot of track lighting divided by 2, that's 10. 10 times 150 volt amps, 500 watts. Okay, 220.18b, inductive and LED lighting. LED was added like in 2014 and 17. Yeah, 2014. Branch circuit for inductive and LED lighting must be sized to the total amperage and not the total wattage of the lamps. What is the maximum number of fluorescents rated at 1.5 amps each on a 20 amp circuit? Okay, lighting is a continuous load. Remember, it operates for 3 hours or more. Branch circuits must be 125% of the continuous load. 80% of a 20 amp circuit is 16 amps. 16 amps divided by 1.5 equals 10 lights equals 15 amps. Okay? Now you can go the other way around and figure 10 lights or 11 lights. If we figure 11 lights, we'll realize it's over 80%. And we'd have to drop a light. So we went 8 from the back road. 16 ounces, all 80% of a 20 amp. That's 125% of the continuous load. 125% of 15 will be just less than 20. Okay, table 220.42. Now, I didn't mention this earlier, but table 220.12 doesn't have the 3 volt amps per square foot for dwelling units. It's here in 220.42. Okay, now the table here tells us that the first 3,000 volt amps will be 100%. The next 117,000 will be 35%. Now, what you got to remember here, this is 120,000. 117 plus 3, this is 120,000. Now if you've got over, you get a calculation that's over 120,000, then the remainder is going to be 25%. Let's just look at an example. Okay, 240.42, you have 130,000. There's my warning sign. This is over 120,000, so I know I'm going to use the 25%. Now this is where a lot of people get messed up right here on the second part. Okay, you've got 130,000 volt amps lighting load. We take the first 3,000 at 100%. Remember I said I like to work with 2 columns. So here's my 100%, 3,000. It's a given. Then there's 127,000 left. We don't do 120,000 of this. We do the next 117,000. If you have to, write this number somewhere around that table. Just kind of scratch it in there. at 35%. Anytime it's over 120,000, you're going to always do 117,000 times 35%. Always. This is a given also. So boom, we do that. The 117,000 at 35%, that's 40,950. And then we'll have 10,000 left over, the remainder at 25%. That gives us this is actually the first step of general lining load. There's actually 3 steps in the general lining load. And I doubt you'll ever get a full question of that, but knowing how it all works together, to me, just seems to help. 46,450 watts. So if we got a 2,300 square foot house, and we do the calculation, remember I told you it's 3 volt amps per square foot. 2,300 times 3 is 6,900. We take the first 3,000 at 100%, and then up to 117,000 at 35%. Well, we only got 3,900, so this is probably the most common for a house. And boom, we've got 4,365. Those measurements are also outside the measurements minus carports and porches. 220.52. Now back in 210.52, it tells us that we got to have at least 2 circuits calculated. You may have only 2 outlets, but we got to have at least 2 circuits calculated for the kitchen, no matter how small it is. Now, here's another thing you might have to deal with cities. They may only allow 3 or 4 or 2 per circuit. You probably won't have more than 2. That's fine. There's a lot of argument. Also, the dining room and any bar area, all these receptacles are considered small appliance load receptacles also. You'll have a lot of arguments on that with some inspectors. And you'll also have the refrigerator on this small appliance load. Now, don't get this confused with the appliance loads. Small appliance is the receptacles, and appliance loads are the dishwashers, disposals, and stuff like that. We'll look at that in a minute. Okay, so you got to have a minimum of 2 of them, and they got to be 1,500 watts each. The laundry load. Okay, gas dryer receptacles, wash machine receptacles, all the receptacles can be on the 1 branch circuit. This is a 20 amp circuit, has to be 20 amp. No other receptacles outside these walls can be on that. Hallway receptacle, nothing. I know a lot of people pull a designated circuit for a wash machine, but if it doesn't pull over 50% of the calculated load, 20 amp breaker, so if it pulls over 10 amps, it's a dedicated load, but normally you don't see that. And then again, inspectors may not allow it, but this is the code. Okay, so the dryer, gas dryer, not the electric, gas dryer, wash machine, all the receptacles in the laundry room, 120 amp branch circuit. Got to calculate 1,500 for it also. The minimum load for a electric dryer, 5,000, 220.54. Now, this trick question here, usually I say, what's the calculated load for a 4,500 watt dryer? 5,000. It cannot be smaller than 5,000. It says 6,000, and you calculate 6,000. It just cannot be smaller than 5,000. 220.53 appliance loads. Here we got a trash compactor, disposal, dishwasher, water heater. That's 4. If you got 4 or more, you can do 75% of the calculated load. So if I got 4, like I showed in my picture, 1,200 watts, 1,000 watts, 1,400 watts, a water heater, 4,500 watts. The total is 8,100 watts. At 75%, our calculated load would be 6,075 watts. Less than 4, 100%. Okay, we're continuing on with this is a complete general lighting load. It includes the square footage, the small appliance load, and the laundry load. This is the total general lighting load. We did each of these by themselves. If I was doing a house calculation, this would how it be done. The 3 volt amps per square foot, the 2 small appliance circuits, the laundry, first 3,000 at 100%, the remainder at 35. We got 5,205 watts for these 3 loads. Okay. Then we would add our disposal, dishwasher, water heater, and so far we've got 12,105 amps. Now we'll do a whole one here after a while, but right now that's 2 steps right there. There is a table 220.54 on dwelling unit dryers. Now this is dwelling unit only. Commercial dryers are 100%. One of the trick questions I've seen on this, how many commercial dryers demand factor is there for 6 commercial dryers? There's not one. It's 100%. Dwelling units, if I got an apartment complex or several units, over 4 units, then I've got a percentage I can do on the 5,000. Cooking. Now this gets a little hard to understand sometimes. Let's just kind of look at the table. Probably want to look at the 220.55 in your code book. The first column is how many appliances. Column A deals with percentages of 3.5 and less kWs. So 1 kW, 2 kW, 3 kW. Column B does percentage of over 3.5 to 8 3/4. Anything over 8 3/4 to 12. Column C. Now column C is already calculated. For instance, if I've got one 9 kW countertop oven, it's 8 kW. If I got a 10 kW oven, it's 8 kW. If it's 11 kW, 8 kW. 12 kW, you're going to calculate 8 kW. Okay? Here, if it's 3.5 to 8 3/4, it's going to be 80% of what it is. If it's 7, then you're going to do 80% of 7,000. Here's some examples down here. Now, as you can see here, we got 3 and 4, so you can kind of see what's going on here. 1 3 kW is 3,000 at 80%. So my calculated load for it would be 2.4. 3 would be 70%. 3 of them equals 9. That's 70%, 6.3. B, 1 kW unit, 4,000 at 8%. That'd be 3.2. 2 6 kW is now 12. And actually under note 5, you can also take both of these and calculate them as 11 kW. This here would be less. The total load for a 9 kW is the load, a load for 9 kW is 8, 10 is 8, up to 12. I said that earlier. Okay, now when it's over 12, you increase for every kW over 12, 5%. Now this was in our Ohm's law. We got 18, we've got 6 over. 6 times 5%, we're going to increase 8 kW by 30%. Okay, so we got to put our 1 in front of it, our multiplier, times 8 equals 10 kW, 10.4 or 10,400 watts. Here's another one, all of them added together. We've got let's see, 8 plus 3 is 3, 14. Okay, this should have been an equal mark here. 14 minus 12, there's 2 kW over. 2 times 5 is 0.10, 10%. Multiplier of 1, so 1 times 8, because we're increasing, we're changing the 12. Remember, the 12 can be 8 kW. That's where this 8's coming from. And we're increasing this by 10%. So 1.10 times 8 equals 8.8 or 8,800 watts. Well, that's as far as I'm going to carry that on there. Normally, if you're lucky, they normally just 2 appliances and you can use a table. Here, commercial kitchen also has a little table. Let's just kind of look at it. Table 220.56. If you got 3 appliances or more, there's a percentage. Here we're using 2 4 kWs, 2 fryers, 1 stove, 6 kW. So we got 5 pieces of equipment. We get to do 70% of the total. Okay, 70% is 12.K. Now it cannot be less than the total of the 2 of the largest equipment. Well, we got a 6 kW and a 4 kW. That would be 10 kW. So we're good. Okay. Now if this number came out lower than 10 kW, then we'd use the 10 kW. Okay. 220.60 deals with not just AC and heating and air, because one load is not going to be on when the other is, so you always calculate the larger. But also with motors, you may have alternating motors. You don't have to do a calculated load for 2 motors, just the largest one. So in our case, it's always going to be the larger of heat and air. And if it's electric heat, normally it's always going to be the heat. So which is larger? We got a 240 volt 4 kW heat strips with a 1/2 horsepower motor at 9 amps. It's a blower. And the AC is 3 horsepower, 230 volts. Okay. The heat comes out to 42 amps. All right. Now if we look up 3 horsepower, 230 volts on 430.240, which we'll talk about in the second video, they will tell us 17 amps. So we just drop the AC. We don't have to enter it in our calculation. We'll use the heat only, the 42 amps. Or if we're adding everything up in watts, we'll change this to wattage and add it to our calculation. Remember 220.61, I know we normally don't practice it, derating to neutral, especially commercial and residential, but the code, National Electrical Code, allows it. You need to understand it a little bit and how to apply it. So the maximum load. So what we have is the neutral load is always smaller because of line-to-line loads. There's no neutral load with water heaters, no neutral load with the heat and air. And so we got 400 amp service, with 150 amps of line-to-line load. That would allow for a 250 amp neutral. Okay, so we can get by with a 250 kc mil conductor for our neutral. Also, 220.61b1 allows 70% of cooking units and dryer loads. Okay, most of those neutrals are strictly for operating the bells and whistles and the lights on the dryers and the cookers, okay, and the ovens. So anyway, you're allowed to do 70% of that load. Let's look at this one for the 220.61b2 over 200 amp neutral reduction. Again, over 200 amps can be reduced by 70% for a 3-wire single phase, 3-phase, for example. What is the service neutral calculation here? We got 150 amps of line-to-line loads, no neutral load. Okay, got 100 amps of cooking, 70% of that. 40 amps of dryer, only 70% of that. And then our little branch circuits, we've got 200 amps of neutral current. Total neutral current, total service is 490. The neutral is only 298 amps. Okay, so over 200 amps. So we got 200 amps at 100%. The remainder, the 98 amps here, at 70% gives us 69 amps. And so our neutral load can be 269 amp conductor. This should be 310/16. I didn't change that, but that's one of the best changes they did in the 2020s. Put this back to 310.16. Why they ever did 310, 15B16, I'll never know. They renumbered a lot of 310 a few code cycles back. But anyway, we get by with a 300 wire KC mill wire for our neutral. Okay, the optional calculation is a real simple way, quick way to calculate a house calculation. It's not as accurate, but you take 100% of the first kVA and 40% of the remainder. You do no demand factors, and if the dryer is 4,500 watts, then you calculate 4,500 watts, not 5,000. So you kind of throw all the rules out the window. You take the 3 volt amps per square foot, the laundry load, the small appliance load, all the appliances at name rating, any motors, add it all up. Take the heat and air, the larger of the two, 100% of AC, 100% of heat pumps. And then these three here, I've seen these 3 questions as just questions on the test by themselves. Heat pump with supplemental heating is 100% plus 65% of it. Space heating, 3 or less, you only calculate 65%. Space heating 4 or more, 40%. So I did one. Just all the straight numbers, add everything up, all the way down, leave the heat and air off for now. 100%, right, 10,000. Remainder 40%, 16,900. Figure out which is the larger, heat or air. Add that. Boom. 29,000. Divide by 240. 121 amp. See, 125 amp service. Number 2 copper. Again, this should be 310/16. Again, if existing calculations. First kVA at 100% to falling 1 through 3 at 40%. General lighting load, small appliances, name rating of fixed appliances, pretty much the same thing, except we do first 8,000 at 80%. We're adding on, we're just doing a general calculation of what's there. And then we can put our add on to what we're going to add. Multiple family calculation. Now the only trick here is the small appliances. You can do it 75% because I've got 10 units. But anyway, these loads are already figured. And then there's a table, 220.84. How many units you have. You can do a percentage of the totals. Okay. No demand factors. There's an exception for laundry at 210.52 ELF, exception 1. You don't have to have a laundry load for your apartments if there's a laundry facilities provided for everyone to use. If there's not a laundry facility provided, you have to calculate a laundry load. That's a good one to go back and highlight in your code book. I've seen that on the tests. Schools. I'm just going to kind of go through these real quick so you can understand this table. It looks very complicated at first, but basically 3 volt amps per square foot. The first 3 volt amps per square foot, 100%. from 3 to 20 volt amps a square foot, 75%, and 20. Let me show you. We do our load of what the school is going to be. And if the school is a 10,000 square foot school and we got 160,000 watts of load, we divide the 10,000 into the watts, and that gives us an average of 16 volt amps per square foot. That's a pretty big service, okay? This is an over calculation. So we take that 16 volt amps and we take the first three at 100%. Here's my side column again. We take anything left over. 3 from 16 is 13. We'll take 13 at 75%, and it drops it down to 12.75 volt amps per square foot. That gives us our service size for our school. This is the optional method, okay? And so we go down here and we worked it all out, our service and everything, and how many amps. Restaurant, same thing, all electric. These look real complicated, but if you just read what it says, here we're using 201 through 325. So I've got all electric restaurant. I'm going to go with 3-phase, 350,000 watts. Okay. All right. Well, 350. This 350 is over 325. Okay. So 350 is 25 over 325. So you take 10% of the amount over 200 plus 160. So actually we use this one. 350 falls in here. I'm sorry. 350 falls in here. 50% over 325 plus 172. All right. 50% of that 25 over equals 12.5 plus that 172.5 equals 185. Then I do my calculations. Square root of 3 on the 208 volts, and we come up with 514 amps. Same thing with not all electric. 300. 300 falls in here. 50% over 200 plus 200. Okay, 300 over 200, we've got 100 at 50%. Anything over 200, 50% equals 50% plus that 50 plus 200 equals 250. Pretty simple. All right, this is the end of this video. Again, call us, email us if you have any problems, and let us know if you passed your test. And we sure thank you.